I'll spare some of my time by avoiding a long description. I just would like to stress 2 points. So we all know about the mass spectrum, which is a kind of power law for the high mass stars. And for me, it's a signature of a scale-free process. The question is to know which one, but probably gravity and turbulence as usual. Okay, and so we have now to agree on the detail of, because there are different ways that they can manifest themselves. And then there is a sudden stop with the peak, which means that there is actually a characteristic mass for the stars, around 0.3 solar mass. And to me, this is a sign that something is actually stopping this scale-free process. And the goal is to understand what is stopping this scale-free process and producing a typical mass. Right, so the plan of my talk will be the following. First, I will investigate to what extent the core mass functions can deliver the initial mass function. And I will present some kind of zooming simulation where I will stress a lot the issue of convergence. This is essentially the history of a failure. And the failure will be extended to a more, maybe, more serious one, which generally speaking, what is the structure in the ISM? Huh? Yeah, I think this is a very serious issue. And then the second, I will argue for the need to actually switch to smaller scale physics. Then I will present a series, systematic investigation, trying to hunt for the IMF origin. And then I will, probably in a rush, I suspect, describe 2 models. One that typically address the question of the power laws. So from the side, the gravo-turbulent picture. And the second, which is the peak of the IMF, which I would argue is due to some well-known physics, which is the dust opacity limit, which produce a change of physics, a complete change of the physics. There is a trick that the mass you produce is 10 times above the mass that you would infer. Okay, essentially, and I will explain maybe in a rush while a model which describes this. Okay. So the core mass function, I think, is known from most people. So again, I will save my time and go fast. So essentially, it builds on the idea that there is a similarity between the observed core mass functions and the initial mass function. And many models, including some by myself, have actually tried to explain the core mass function from gravo-turbulence, essentially. So in an effort to try to obtain as self-consciously as possible the core mass functions, we need to somehow get rid of the initial conditions, because initial conditions are always a problem. So you want to essentially find ways not to prescribe the initial conditions, and this you can kind of do by doing this kind of kiloparsec box, which have been done by several teams, where you have essentially stratification. You start just with wall neutral medium, and so all the dense gas is formed from this feedback regulated setup. And then the idea is when it's sort of sufficiently advanced, you can identify the region of interest, and then you can zoom. Okay, so this way, the initial conditions are due to the physics you put in, and they are not put by hand, so to speak. So that's an example of this. So in these simulations, we were able to go, say, from the kiloparsec up to 2⁻³ parsec, okay, meaning that we cannot describe the internal part of the core, but cores as entities, if this has any sense, are described. Okay, so essentially all these little points here would be a core. So then you get a lot of statistics, and you can build a mass function, a core mass function out of that. And at first look, it looks encouraging. there is something like yeah, salpeter. I mean, salpeter is not very accurate neither. You have a peak, which is too high, but still there is a peak. Of course, when you do simulation, the first things you have to worry about is the effect of your numerical scheme. So the first thing you should do is increase the resolution. And when you do that, you see from here, so Lmax here is essentially the maximum level of refinement. You see that your peak happily goes to lower and lower scales as you increase your resolution. And that's the same actually result found in this other paper by Pelkonen et al. So this means that the core mass functions is completely artificial. It's due to the lack of resolution in your simulation. And well, I don't know whether it's unfortunate, science is how it is. It turns out, I would argue it's also the case for the observation. That's based on the work that Fabien Louvet had been doing in collaboration with me. So essentially what we did, we took Herschel maps and also MHD simulation maps. Okay, so you took a map and then what you do is you say, okay, any result you extract from simulation, from observation, must be robust to a change of resolution. If it depends on your resolution, then you have to argue why your result is just at your resolution. Otherwise, you may say, well, then it's resolution dependent. So what we did is we actually smooth those maps from simulation or from observations 2 times, okay? And then we did the core extraction exactly as the observer do. Same algorithms using the software developed by Sasha Menshikov, GetSF. And you find exactly the same story than in the previous, than in what I just showed from simulation. The core mass function happily follow your resolution. Okay, so there is a possible encouraging news, so to speak, is that the slope itself may be more robust. We actually tried to measure it as well as good as we could, but the peak is not. And so the core are completely elusive objects. So I would say the CMF theory is possibly successful in predicting the high mass part. It failed to reproduce the robust peak. It means that we need to change strategy and identify what mechanisms can really set a robust peak. Okay, so far I would conclude that from the standard ISM cooling, MHD, gravity, stratification, feedback, nothing is able to do that unless the simulations are badly wrong, which is of course always a possibility. But given what we observe also on observational map, I think it just makes sense. You have a self-similar structures typically due to graviturbulence, and it just fragmented and fragmented and fragmented up to the point where you will eventually find something robust. And what can be something robust? We need to get back to very simple physics. If you compute in a general, so this should be a gamma, sorry, in a general framework, the ratio of thermal over gravitational energy of simple clouds, you quickly figure out that there is a critical exponent, which is 4/3. Okay, if gamma is larger than 4/3, you have something like a star, meaning that as you contract, the gravity is less, increase less rapidly than thermal support. And so you will stop any fragmentations. So we have to chase where in the ISM do we get an effective adiabatic exponent of 4/3 and see whether it can be anyway related to the IMF. And as I mentioned, there is one case, obviously, the first density at which it occurs, starting from diffuse densities and going to denser one, is precisely when the dust becomes opaque to its radiation, where you get an effective equation of state, which is stiffer than 4/3. So I'm going to describe a series of simulation, starting from essentially a prescribed cloud. So unlike the other attempt trying to get rid of the initial conditions problem, I will address this time by essentially varying systematically all parameters that you could think of and try each time to understand what it does, okay? So this type of simulation has been done by several people in the room, so including Javier and Lee, but also Jan. I've been doing that for many years, and I would say make great progress on that. I mean, they were, in particular, Jan has been pioneering this subject. And so you find from the simulation that there is a diversity of behavior. First, I would say it's difficult, in my opinion, to argue about salpeter here, but you see the peak here is at much lower, than masses and than the observed one. So there are issues, and this needs to be, I would say, investigated in a coherent manner, which is now allowed by the increase of computing power. So we have conducted in a series of papers something like a systematic investigation. So essentially, we set up 1,000 solar mass clouds, which is a compromise between resolution and statistics that you need to generate an IMF. If you have a bigger clouds, well, then you have to go deeper in scale, and this is more challenging. We have either a simple prescription to describe the transition between isothermal and adiabatic by using an effective equation of state, or we also do full relative transfer calculations, which tends to confirm that it is actually, for that specific purpose, relatively okay to use the equation of state. Of course, there are many, I mean, there is a source of heating and so on, which may play a role. I'm not focusing on that today. So yeah, just to, I don't know, my arrow is up here. So just to summarize here, so you have here isothermal, and at the beginning of the process, yeah, your effective equation of state is 5/3. So the simulations will go up to 1 AU resolution. Okay, there will be a systematic investigation of the impact of the resolution each time. Okay, and then we will vary independently the density, the turbulence, the magnetic field, and the equation of states, and each time by orders of magnitudes, not just factor 2. Okay, right. So this is the first example. I will not show you many variations because it will be boring and it will take time. So I'm concentrating here on one case. So we vary the density. So each panel here corresponds to one cloud with one density. And so the various lines, they correspond to different time and mass converted into stars. So initially, the density is kind of low, 10 to the 3. And we go up to like 10 to the 7 here. Okay, so 4 orders of magnitudes. And so which correspond also in terms of dimensionless number to the ratio of turbulent and thermal energy, so which means the Mach number. So we go from low Mach number to high Mach number. So first, here you see at this first simulation, you barely see something which looks like the IMF. It's completely flat, m to the 0. Okay, so, and I think it's something important. I will tell you why, because I think if you want to probe your theory, if you say, okay, I explain this, blah, blah, this must be also explained. Okay, so you must come with a theory which also explains that, not only salpeter or something, okay? And then as you go to larger density, well, then you start seeing something like a power law, which actually is a bit too flat. It's more, I would say, 3/4 or 1, rather than 1.3. And then, interestingly, from this point here, as you increase your density further, your peak does not change. It stays the same place. Okay, and your whole mass spectrum does not change significantly. So, for instance, what this allows to conclude is that once you reach the stage here, you cannot argue, for instance, that the peak is due to the Jeans mass, because the Jeans mass changed by enormously here. Okay. So the second thing, as I said, you should do immediately is change resolution. Okay, we saw there is a very severe resolution issue in this business. So we saw a peak. We must understand whether this peak is meaningful. Okay, what's behind? So first things, you can run isothermal simulation, and you find the same story repeating itself. If the simulation is isothermal, as you crank up the resolution, your peak shift to lower and lower masses. And the reason is simple. The Jeans mass goes like the square root of rho, I mean, -1, the square root of rho. If you increase rho, well, then you get to a smaller peak, essentially, and a peak which is limited by the numerics. If you have now a standard equation of state, meaning that you allow from isothermal to adiabatic, then this time you see something which does not depend on resolution. You increase the resolution here by a factor 4, it's still at the same place. So it seems to indicate that indeed the transition from isothermal to adiabatic is fundamental to set the peak of the IMF in a way that we need to understand. So to do this, you can change, you can vary your effective equation of state. Of course, in physics, this is dust which control that, so it would not vary a little bit if you go to different metallicity, but essentially, this is a numerical experiment to investigate what's going on. So you can play around, for instance, with this adiabatic density at which you switch, you introduce this transition. And as you see this time, when you modify the adiabatic density, you see the peak shifting toward higher masses. For 10 to the 9, here you see the peak occurs at 1 solar mass. Okay, so it shows that the peak, A, it's converged, B, to a large extent, does not depend too much on your initial conditions if you are in some regime, and C is controlled by the thermodynamics at small scale. So to try to make it even more quantitative, we vary even further the equation of state, and we compute the mass of the so-called first Larsen core. So this is the hydrostatic core, which forms when the dust becomes opaque to its radiation. You have an adiabatic core, so gravity is stopped by thermal support, and you start building quasi-static core up to the point where finally you will dissociate H2 to form a star. And so you can compute for each equation of state, you can compute the mass of this core here, okay? And then you can draw the mass of this core and the mass of the peak in your simulation. So this is from theory that's calculated. You have an equation of state, you can calculate your mass, and this is what is measured in simulation. And you see a very nice correlation between the two. There is, of course, dispersion, but essentially, so it's proportional, but 10 times larger. Okay, so I'm in the remaining 5 minutes. I will try to present two analytical models, which for now are kind of decoupled. I think the goal at some stage will be to kind of try to unify them, and I think it's a challenge. So the first one is an attempt to understand the power law of the mass spectrum. And the second one will be to understand better why we have this factor 10. What's the meaning? What's the physics behind this? So first, regarding the mass spectrum. So the idea is we do a scale analysis where we write essentially that there is an equality between the mass which at the scale R is unstable to gravity, and the mass which ends up in the structures which have a mass smaller than the Jeans mass at scale R. And because scale R is a continuous parameter, you can take the derivatives, and then you get the mass spectrum as a function of your density PDF and the physics which control the unstable density at scale R, which essentially will come from the Vial theorem. And so you see there is a direct link between the mass spectrum and the density PDF. And so the density PDF, we used to take initially a log normal density, but as you know, it has been presented before in several talks, there is actually a power law also, which is there. And this power law is due to gravity. Essentially, you have the collapse of the structures, which develops a power law, rho proportional to the minus 1.5. So there are actually two regimes, okay? The regime where the PDF is set up by, I would say, gravoturbulence, and the regime where the PDF is set up essentially by gravity, by turbulence only. So it turns out that if you just apply these formalisms, and in this case, just asymptotically to make it clear, so you have a mass size relation of your reservoir, the one that eventually determines the mass of your star, which is controlled, I would argue, by a combination of thermal and turbulent supports, which kind of resist gravity and determine the coherence of your reservoir. And if you apply this using this power law here, you find that if thermal support dominates, you do expect a mass spectrum which is completely flat, m to the 0, which is the first simulation I presented. And if you, on the other hand, consider a higher Mach number core, I mean clamp, with turbulence, then your support is scale dependent because turbulence is scale dependent, and then you find m minus 3/4, which is consistent with the second mass spectrum I presented and which doesn't depend on density. So I would argue our mass spectrum are due to the competition of, on one hand, gravity with fluctuations set by gravoturbulence, and on the other hand, to support thermal and turbulent. And to check this further, we have been looking at the accretion rate in the simulation. So the red points are the mass of the sink as a function of their lifetime, typically. So essentially, this is an accretion rate. And the curves are the accretion rate predicted by this reservoir theory I just described. So essentially, you have a free fall, okay, and the free fall entails the density, which depends on the competition between thermal and turbulent support. So you see, essentially, up to the 0.1 solar mass, typically, you get the right trends. Okay, even so, you change the density by a huge amount, you get the right trends. You don't get it below 0.1 mass, solar mass, because you change physics. It's no longer isothermal, it's adiabatic. So it's a different story, okay? But so essentially, I would argue that this actually is a sign that you have coherent gravoturbulent reservoir. But there is a hierarchy of interwoven reservoir, big reservoir inside small reservoir, which makes that the whole picture is not simple, I would say, okay? Okay, and finally, in the remaining few minutes, I would like to explain how do we go from a mass of the hydrostatic core, which is essentially 3 × 10⁻² solar mass, and which is the mass of the first Larsen core, the hydrostatic core, which is due to the fact that dust becomes opaque to its home radiation, and a peak, which has 0.3 solar mass. The issue is that once you build one of those cores, so like this, you are actually in the regions which is around is not a very good place for a new fragment to form. It's actually difficult for a new perturbation to go through and form a new stars. And the reason is that not only you have the gravity of this object, which exerts destroying tidal forces, but you also have an envelope, R-2 envelope, which has also negative tidal forces. So if you want to go, if you are yourself a density fluctuations which try to find your way up to the star, you have to fight not only your own support, but you have also to fight the presence of tidal forces. And so we build a model where we ask two things. Perturbations to go through must have at least the mass of the first Larsen core. Otherwise, you don't dissociate H2 and you don't form a star. And B, you look your gravitational energy, including the tidal forces, must be negative. So you have these two criteria. And so you have now to build the statistics. If you have fluctuations developing in the vicinity of your object, you have to count the statistics, you have to count the fluctuations which supersede or which satisfy these two criteria. So it's a bit of a technical calculation that I'm not going to present today. It's described in this paper here. I would be, of course, happy to discuss it with some of you. So is it a pure view of my own models? Well, at least there is a paper where I'm not involved, where they try to verify this. They essentially, around each sync particles, computed the regions which is tidally protected. So meaning that the tidal forces will just remove, prevent fragmentation. And by computing the mass spectrum of these tidal sort of protected regions, they can compare with their final sync masses, and they find a sort of good agreement. So the physical picture behind is that once you have accreted your core, it's very difficult to avoid accreting further away because all these regions here is protected from fragmentation, so it's going to collapse in the center. And the ratio of the mass which is protected and the mass of the first Larsen core is roughly a factor 10. Okay, so this is our explanation. And with this, I think I'm done. So just trying to synthesize the most important conclusions. So as far as I can tell, the diffuse ISM physics does not provide the ingredient for a robust peak. The CMF is not converged in observation and in simulation. It may still be important to explain the slope. This I did not discuss today, the relative feedback. And so the general proposition for the power law of the IMF. So the power law is due to gravoturbulence, essentially. So it's a competition of thermal and turbulent support on one hand, and a log normal versus a power law on the other hand, which produce a diversity, some diversity in the mass spectrum we can get. And regarding the peak, I would argue that it is due to the dust opacity complemented by tidal forces. I thank you for your attention.
Well, thank you for perfect timing. So there's time for questions. Okay, Lee. Well, you're the honored one. So.
Just is this thing on? You know, I would say in terms of the power law that maybe you're looking at it the wrong way around. That is to say, if you just have, gravitational driving where you've got, like in competitive accretion or whatever, that's the thing that gives you the density power law that you have, right? So if you think about the density power law is a result, but not a condition that's driving the whole thing. It's really gravity is what I would say. But I want to, so that I'll bug you about that perhaps at some other time. But if the tidal limitation is good, and that's a really interesting idea, we look at very dense, a wide range of density of star forming regions, right? And so shouldn't we see different mass peaks as a function of density of the star forming region? If we look at Taurus, if we look at Chameleon, we compare it to the ONC, looks like the peak is in the same place. Is that insensitive then?
No, I think it's precisely, I think that's the reason why I consider this as a good candidate. You know, I always try to disprove myself very strongly. So when I'm saying I think it's a good candidate, I'm not saying that I'm correct. It's just that I tried to kill it. I tried to kill it myself several times and I failed. So no, what I'm saying is that this is actually extremely small scale physics because it depends only on the dust, which is like 5 AU-ish. And by this time, you know, the gravitational collapse, it's, as Enrique explained, almost R-2 with a free fall speed. So you still have some variations, and there's a bit of compensation, but I would say it does not depend on the detail of the, or very weakly on the detail of the large scale collapse because it is all small scale. This peak is set at below 100 AU. This factor 10.
So we have now one from the Zoom.
Yeah, there's a couple of comments on Slack that you might want to address later, but the first question is via Zoom, and it's Hans Zinnecker with your hand up.
Hello, Hans.
Okay, well, very interesting to follow all this from a large distance. Okay, so I enjoyed the morning. Now, Patrick, what you have told us about the peak of the IMF, is that in your explanation, is that any different in principle or in detail from earlier ideas of Jabson, Klesen, Richard Larson, Matthew Bate, and even Krumholtz? So
yes.
What's the difference?
So Jabson and Klesen, for instance, they consider the transition, or Larson, they consider the transition between the gas, which is cooled by the molecules, and the gas, which is cooled by dust. And that make a change in the equation of state between gamma 0.7, 0.8 to 1. Okay, and in terms of the change it makes on the equation of state, it's actually very little, because what is crucial is 4/3. Okay, 4/3. Then, okay, I have to quote all papers that you mentioned. Then regarding Matthew's work, there is a paper for Matthew, actually 2000 something, where he argued that the equation of state is actually not important for the peak. And the reason is because he used gamma equals 7/5, and 7/5 is very close to 4/3. While at the early stage, when you become adiabatic, your equation of state is 5/3. And this makes a lot of difference in terms of the density dependence on the Larson cores. And you mentioned also Krumholtz. So Mark is actually arguing that the feedback is making the IMF, and I would argue that the feedback is not making, well, sorry, the peak of the IMF. It has an influence, it hit the cores, and maybe for the mass of the most massive stars, it's important. But as you show in the slide I just put on the screen, and from the 2020 paper, essentially, if you vary if you compare the IMF you find with a purely baroscopic equation of state and with a full radiative feedback, you find very similar results. So I'm not saying that this is brand new, and I would like to insist that addressing a problem as complex as the ISM is necessarily a collaborative project and a collaborative work. And people, again, in the room, like Jan and Javier and so on, they all have important, and you also have important contribution. Okay.
So we have time for a quick question by Jan.
Thanks.
Thanks, Patrick. I want to make just a quick comment and a question. The comment is, I like your title stuff. It reminds me a lot of what Round Smith found for a thesis, where you'd got a cluster forming, and for young stars forming inside there had to be very dense clumps falling in. So they were tidally okay. And the rest of the mass, which wasn't that way, would then be contributed to the forming massive star in there, in that kind of picture. So it sounds very similar to what you're finding there. In your mass function, when you go from a mapping from the PDF to the mass function, one thing always concerned me is there's no guarantee that the elements are real. So you can have a core, which is a high density, and you've got stuff around it, which is low density, which in your mapping then goes into a high mass star rather than as an envelope around a lower mass one. And so that element, when you lose the spatial bit, always concerns me.
I have a cartoon where we discuss this with Enrique during lunch. Actually, what we tend to agree on, I think, is that you get a hierarchical sort of distribution of gravitational well. And so inside all of this well, you will start sort of accreting preferentially the first well, okay? You possibly have some kind of competitive accretion inside the well. Actually, I think there is an issue, and I think that's what Lee wanted also to discuss, between deterministic and stochastic picture of star formation. And I think the final answer is probably both or in combination. And we have to decipher what is more deterministic and what is more stochastic. And I think this work needs to be done. And so as you have finished accreted the first well, then you will go to the second one. But then, of course, you are out your first well, but you are still deterministic with respect to the larger one. Okay?
Okay, thank you again, Patrick. Okay, and the next talk is an online talk by Tyler Burke. And it's an observational talk on the same issue, masses. How do stars get their mass?
All right. Well, I wish I could be there in person, but I will give this talk from just across the Irish Sea near Manchester. Yes, I'm going to talk to you today about a program, primarily SMA, called Masses, or to put it succinctly, how do stars get their mass? Okay. So we sort of hopefully all agree on this general cartoon of star formation, low mass star formation in particular, where we see these snapshots in time and in scale. We can debate the details of how this proceeds in time, and that's exactly what motivates this sort of program. So while we have this sort of these snapshots, what we really want to know is what sets all the transition points, how does core formation happen? What starts and ends accretion? How do multiple forms, for example? And so it leads to the general overall question of how do stars, protostars in this case, get their mass? And when you ask a question like that, then there are some smaller questions you can ask to get to that point. And in particular, ones we focus on is when does protostellar accretion essentially complete? Are outflows regulators of accretion? That's been an idea that's been thrown around for a while without much evidence for that. On what scales do protostars inherit their environmental properties? And how and when do multiple star fragmentation occurs? And when you can see these questions, when we started this project, we realized that to do this, we need to have finer resolution on the small scales, going from the cores to envelopes to the disks. And a lot of work had been done in sort of a heterogeneous way. So it's best to have, we can complete sample statistics in a sort of more homogeneous manner, because many observables have broad distributions. So I want large numbers to look at this. But before I get into the talk, I just want to touch on some of Lee's influence on this question and my career in particular. Some years ago, I did ask Lee to give a talk at a meeting in Sydney almost 20 years ago now And I threw the title at him. I said, I want you to talk about testing the paradigm of low mass star formation. Okay. Someone earlier in the day showed a picture of Lee, was wondering, well, what's he thinking? I can't figure out what he's thinking. Well, I know exactly what Lee was thinking because he told me. You want me to do what? He didn't say it in quite such a nice way, if I recall correctly, but that's quite okay from Lee. We could also say Cesar and Nuria there are also asking some questions, but even Lee's abstract back then was touching on the key points, and it's been talked about with the famous 2001 paper. This is from 2004. Core formation is probably much more dynamic. Magnetic fields are probably much less important than believed. And we need to get to look at the structure and asymmetry of sort of the protostars being formed to see what happens in terms of fragmentation. And as I mentioned, the sequence of events for star formation, low mass star formation, is not really controversial. What we needed to get at with the details, and Lee's already talked about that, these transition points, these endpoints. You can just read it here yourself. At that point, Lee was always talking about filaments and fragmentation in the pre-Herschel days. And I don't think Lee would mind if I said that he's probably thinking to himself, well, what's this guy talking about seriously? And one aspect that has also been touched on today was the idea of a Bonner-Ebert rectangle. And Lee rightly pointed out in this talk, which is one of the reasons I asked him to give a talk like this, just to point out some of the problems, is that at the time we didn't have very good sensitivity and resolution for looking at cores. And so a lot of people are doing circular averaging. And if you do that in this sort of way, you can come up with a Bonner-Ebert sphere from something that looks rectangular. This is the sort of time when we were transitioning to the point where observations, and here's a nice example of a starless core with SCUBA, these nice observations were coming out and we could start to model them in more detail. We could go from what would previously be just sort of a power law fit, a very simple circular averaging back in 2000, looking forward to where you start to do more complicated structures. And we've progressed a lot more since then. So some shameless advertising here for a recent paper led by Paula and Jaime on ALMA observations of L1544, where we do look at a structure to model the observations that is at least better than 1D. And if you compare the observations up in the corner on the right here, top right, compared to the a model which has been observed with ALMA simulations in down bottom left, they look pretty good. And the difference between them, that does look like just noise. So we're going in the right direction, Lee. We'll get there. All right, back to masses. So the motivation for doing this large program was to look at the 74 or so class 01 protostellar systems in Perseus, in the submillimeter line and the continuum. These are the same targets that were being observed that time with the VLA by John Tobin in the about a centimeter or so wavelength. We had about 6 hours of time on the SMA, and we paired that with a nice Origins grant to fund some of this work. You can read the specs here. We observed at 230 gigahertz primarily, with some 340 gigahertz resolution, about an arc second or so at Perseus, which is 300 parsecs away, and a focus on these 4 lines at the top with a bunch of other lines. So why Perseus? Well, nice thing is that that has about an equal number of class 0 and 1 sources. They're very well sampled SEDs, thanks to all the great infrared and far infrared missions. I think it's relatively nearby. It's very well positioned for the SMA to observe. And it's sort of a mix of sort of clustered and isolated star formation. So you get to look at that environmental aspects. That's just the team there. I won't go through that. You can read that later on. You can see the papers. The main point I would like to point out for this slide is that the data, or the reduced data, is all available online at this web link. So you can go there later on and have a look at that. And there's a couple of data papers. There's this one here, and more important, the second full release data paper describing basically how you get the data and how you can use it. And a sort of a rogues gallery, a bunch of outflows on the left in CO2 to 1. And what you can't see there in black are the continuum emission from those same regions. And then on the right, some integrated intensity maps of the C18O 2-to-1 envelopes, which is a paper which is just about ready for release. So let's just have a quick look at accretion and outflows. So we have this idea here of going through the classes from class 0 when most accretion happens to class 1 where it's still a little bit happening to class 2 where there's not much going on. And they're sort of measured by these bolometric temperatures, and just to remind you of how you get that down here. Similarly, there seems to be some evidence that outflows are contributing somewhat to the structure around these sources, these different classes. Early work done by Hector Arce and Anila Sargent, very limited samples and a very heterogeneous sample here, but seem to indicate that the outflow angle is increasing with the bolometric temperature. And they seem to be evolutionary in some sense. T-bol has often been used as an age indicator, but how these two parameters actually are related to time is not 100% clear. So what can we say more with a bigger sample? Well, we have here, we're extending the work of Hector and Anila with much better statistics. So we have a lot more sources in one cloud. So we're looking at the question of what can stop accretion. And we have 3 separate results which point to a very similar answer. One result shown in this slide, which is still under preparation, is that the outflow angles still seem to increase with time with T-bol until some sort of turnover point around about 100 or so, or maybe a bit less depending on how you fit this. So this is basically Hector's work with a lot more sources in there, so it confirms that result. The next result is to look at how the outflow direction, shown in this little cartoon here, and the angle between that and the long axis of the core evolves over time, if it does at all. And we can see here that certainly in this low T-bol stage, we see the angles are widening over time very quickly and then become essentially flat. So 2 similar results there: outflow angles and angles between the outflow and the core widening until about the transition to the class 1 phase. And then similarly, you see the envelope mass here as a function of T-bol also decreasing till there's basically not much envelope left, and that transition also happens around the 100K time. So, and the conclusion coming out of this, all 3 areas point to the outflow opening until at such point the envelope can no longer feed the disk plus star. So most of the accretion is happening already in the class 1 phase and not much in class 0 phase, and not much in class 1. Another aspect we looked at with these data was outflow directions. Is there any correspondence with outflow directions and sort of by proxy rotation axes? Are they aligned in any or somehow correlated with the filaments that we all know exist throughout these clouds? So with masses, we take our filamentary structure, we take our clumps, and we fit them in sort of a normal way with these filaments using one of these filament finding algorithms. And then at the position of the protostar, we measure the direction of the filament in that little box and compare that to the outflow direction in that same area. So if we do that over all our targets, we come up with this red distribution here, and you can compare that to the cases where they're either parallel or not parallel or just random. And we find that a random fit is a best fit here. So we find that the outflow directions, there's no clear correspondence with the filaments, so the outflow directions are not set on filament scales. We also have a lot of multiple systems, in this case, some wide multiple systems, so we can look at as well to see if there's any alignment of the outflow and so the angular momentum vectors. So we might expect that there's some sort of alignment if these 2 structures appear from a common envelope that's rotating and as becoming Keplerian. So what we have in masses, we have 12 systems, so we have 19 pairs to look at. And again, so there's sort of the rogues gallery. Again, we see the cumulative distribution here is pretty much either random or anti-aligned, somewhere between that sort of value. Here's some bunch of simulations done by Stella Offler and her group to sort of show that this is not just a projection effect. They can do this in 3D and compare to the distribution to show that either random or anti-aligned is the way to go. And so we conclude from this that also that the outflows really aren't set on these envelope scales. And it may be that we're seeing evidence here from turbulent fragmentation of the cores into the individual protostars within these systems. Let's look at fragmentation. The questions we sort of ask here is, what is the origin of the hierarchical structures we see in clouds? And if we can look at this, what's the dependence of each of these scales on gravity and the different pressures? In Perseus, by combining the masses work we have here on the envelopes primarily with information on other scales. In this case, we have the cloud. We take the near-infrared extinction map up here on the right. Clumps are from the Herschel dust emission, and then cores from scuba, okay, and then tying in the VLA observations from Van Dam at the protostellar object level. So we can look at these different levels, and at each level we count the number of observed structures and we compare that to the genes number at each scale. So how many genes fragments could you have? What we find at all levels here is that the number of child objects, so the number of objects at each level, is less than the predicted from the genes analysis. Okay, and what we do see, and what we do see here is that as you go to smaller and smaller scales, actually these numbers get closer and closer together. And so if you look at this as an efficiency, a gene's efficiency, for example, you get to about a factor of 0.5 on the smaller scales. So we call this inefficient genes fragmentation. If you add in a turbulent component, you don't do any better. So that, and actually you probably do a little bit worse. So here's a nice study with over 5 levels where you start to see that the thermal genes fragmentation become more and more important on smaller scales. And finally, on angular momentum, we want to know, is angular momentum conserved on each scale? Is there a problem? And do the cores and envelopes have any memory of the large scale? So other studies have shown, for example, that the specific angular momentum seems to follow some sort of power law with this sort of exponent of P to 1.6 to 1.8. In a purely turbulent situation, it'd be 1.5, and a solid body rotation, it would be 2, so that somewhere in between there. And some studies also suggested that there's some transition at small scales down to some conserved angular momentum, so it basically becomes flat. So a result that will be out soon, so keep an eye out for it, is that with our data, we can extend these plots down to much smaller sizes than have been done before, combining with data that's already out there in the public domain. We do find this 1.8 law again down to about 500 AU scale, so getting quite small. Similar results to some more recent work, actually. We are getting down to much lower values of the specific angular momentum than other studies. And it's also not clear at this point whether our results show that it continues to much smaller scales or if there's a flattening at small values. The fits here have about the same, are about the same in terms of how good they are. So it's still an open question. But getting down to these small scales, these results seem to be consistent with the small observed disk sizes in class 0 phase, and maybe consistent with angular momentum being acquired from the parent structures. And maybe there is no angular momentum problem down to these sort of 500 AU scales. So I just want to leave my summary up. Any misunderstandings are completely mine. You can go back later and look at all these great papers that all my collaborators have written. So I will not go through the summary. You can read it and we'll take some questions.
Okay, thank you,
Thanks.
Tyler. And we have time for maybe a couple of quick questions.
Can you hear me? A very
Yes.
interesting result. So in our Orion B data, we also see the angular momentum is not conserved down to around like 400 AU scales. So do you think that the turbulence is setting the angular momentum of these cores if it follows the slope of 1.8?
That would be the sort of, I guess you'd say the obvious answer, but I don't know if that's the answer.
Okay, Lee?
You didn't mention my argument with Frank at that meeting.
No.
Um,
You can talk about that over beers later.
Yeah, right. So I'm a little push back a little bit about the outflows, cleaning out the mass, because you need a total opening angle of like 120 degrees to cover half of solid angle, right?
Yep.
And when you see the numerical simulations, it actually the stuff tends to come in more on dense structures that aren't filaments and streams and stuff that aren't really spherically symmetric. So unless the outflow is really aligned, I think it might be harder to stop that stuff from coming in than just from a general perspective.
Yeah, so my only comment on that is that this paper in prep, Mike is working on some of the numbers to see what sort of mass and areas could be taken care of by these outflows. So we don't have a conclusion on that part yet.
Next, no? Okay, perfect. So no more questions. Then thank you, Tyler, again.
Okay, thank you. I'll stop.
And next we have Laura Venuti talking to us about multicolor variability of young stars across the mass spectrum. Laura.
Okay, thank you. And thank you to the organizers for giving me the opportunity to present our work. So in this talk, we'll discuss the properties and the timescales of variability of young stars and how these vary across the stellar mass spectrum. So variability is a defining feature of young stars, both all along and beyond the lifetime of protoplanetary disks. And signatures of variability in young stars are observed at any wavelength from the X-ray to the infrared, and on many different timescales from fractions of hours to months and years. At a very basic level, the variability of young stars can be driven by distribution of magnetic star spots at their surface, which induce a modulation effect on the luminosity that we observe as the star rotates. But for stars that are still hosting an active accretion disk, a more prominent source of variability is the interaction between the star and the disk and the flow of accretion from the inner disk onto the star. And these different sources of variability, which are often mixed in the light curves of young stars, are also filtered through the exact viewing angle to each individual star disk system. And variability is a crucial tool for us to understand the physics of the inner disk, because the star disk interaction develops over special scales that are so small that they are really hard to resolve with direct imaging facilities, even for the stars that are closest to us. Therefore, in order to achieve a direct window onto the dynamics and the evolution of inner disk process, a most direct tool is to, first of all, reconstruct the emission of the star disk system across the spectrum, monitor the variability of this emission on different timescales, and repeat this exercise for large samples of coeval stars in young star clusters to study the statistics of these inner disk processes. And in recent decades, many space telescopes such as Spitzer, Crow, and Kepler really revolutionized our understanding of variability in young stars, because they provided for the first time the uninterrupted and long baselines and the photometric accuracy that we need to resolve the small scale variability structures in these light curves. So for the first time, thanks to this service, we were able to really parse the different timescales of variability which are associated with the distinct behaviors of young stars. In the course of this service, the targeted clusters such as MGC2264, Rho Fucus, and Upper Score, we were able for the first time to define a statistical metrics to classify distinct variability behaviors in young stars by observing how periodic or repeated the variability features are across the light curve, across the baselines provided by the space telescopes, and by studying how symmetric the flux variations are with respect to the typical luminosity level. That is, whether there is a prevalence of brightening events, fading events, or neither. So if we move along the periodicity axis, the morphology of light curves that we can detect can vary from strictly periodic and quasi-periodic to purely stochastic. And if we move along the asymmetry axis, we can observe variations in behaviors from dipping behaviors to bursting behaviors. So these earlier campaigns allowed us to identify at least 8 distinct variability types among young stars with disks. But these surveys were mostly confined to lower mass stars, spectral types or K2M. So it is still to be understood whether the same paradigm that was defined for these young stars also applies when we move to higher mass regimes. So in order to address this issue, we started a campaign of variability monitoring in the Lagoon Nebula region, which is a very well-studied young star forming region, which hosts an extremely young cluster, the NGC6530 cluster. This region was the subject of many different studies using a variety of techniques, from the infrared to X-rays, UV, and spectroscopic and astrometric surveys. And in the course of this service, thousands of cluster members or candidate members were identified with an estimated disk fraction of around 50%. In 2016, the Lagoon Nebula, the core of the Lagoon Nebula, where NGC6530 is located, was observed with Kepler during K2 campaign 9. So in the course of this campaign, we were able to obtain high quality light curves for around 300 of the youngest stars embedded in the core of the campaign of the nebula, and with covering a spectral range that goes from B to late K, or masses from fraction of a solar mass to about 5 solar masses. And simultaneously with the K2 survey, we also monitor the variability of these young stars from the ground using a variety of facilities. In particular, in this talk, I will focus on the multicolor photometry from the U band to the I band that we obtained with the VLT survey telescope. And this color information will be crucial to assess the physical origin of the variability that is traced by the K2 light curves. So in our K2 sample, we were able to retrieve all distinct morphological categories of light curves that were identified in earlier campaigns, although the distribution in type varies somewhat from earlier results. So in our sample, in particular among disk-bearing stars, we found that around 50% of stars exhibit a regular modulated behavior, so between periodic and quasi-periodic, and with flux amplitudes that are typically of the order of 25%. Around 20% of our stars exhibit a erratic behavior, either stochastic or bursting, with variability amplitudes that can vary from 50% to 125% in flux. And 15% of the stars exhibit a dipping behavior, with amplitudes that can range anywhere from 75 to 100% in flux. And what we observed in our sample is that the distribution of light curves types across our sample is not uniform across all spectral types. In particular, we observed that flatline light curves, where the variation in flux is just at 3%, are more common among earlier type stars, particularly ANF, than later type stars. And also strikingly, dipping behaviors were found to be largely absent among stars earlier than G. We studied the distribution of different light curve classes across different color diagrams from the infrared to the UV in order to assess the origin of the observed variability behaviors. What we found is that, consistent with earlier results, periodic and quasi-periodic stars typically show infrared colors that are consistent with being photospheric in origin, whereas bursting, stochastic, and dipping stars typically show infrared color excess compared to the photospheric levels, which suggests that these variability behaviors are triggered by disk-related phenomena. And if you observe how the infrared excess varies from the near infrared to the mid infrared, we can get some indication on the location in the inner disk where these variability behaviors are triggered. For instance, we observed that stochastic stars exhibit more prominent infrared excess in the reddest filters than other disk-dominated variables. So this suggests that a stochastic behavior is triggered beyond the innermost disk regions where, for instance, a bursting behavior is triggered. We also studied how these stars are distributed in UV colors, which trace the excess luminosity from accretion shocks at the stellar surface. And what we observed is that, consistent with earlier results, bursting behavior is triggered by more intense accretion activity than the typical amount of accretion we observe for disk-bearing stars in our sample. Regular modulated behaviors, such as periodic or quasi-periodic, can be understood simply in terms of spot modulation along the stellar rotation period, either by magnetic spots, which can cover up to 40% of the stellar surface, or by long-lived accretion shocks in a stable scenario of star-disk interaction. For erratic behaviors, however, the light curves that we observe match the theoretical expectations for young star-disk systems that interact in an unstable fashion. So in these cases, the morphology of the bright spots, the accretion spots at the stellar surface, can change on time scales shorter than the rotation rate of the star, possibly due to a time variable mass load onto the accretion columns. And this triggers the short-lived variability features that we observe in these light curves. As I mentioned earlier, dipping behaviors also appear to be triggered by disk-related phenomena. So in these cases, what we believe is happening is that the star-disk systems are observed in a particular inclination close to edge-on. So in these cases, the part of the stellar surface is occulted by inner disk structures, which can be associated with accretion columns. In this scenario, a periodic or quasi-periodic dipping behavior would correspond to a stable mode star-disk interaction, which would correspond to a quasi-periodic behavior for the same star observed at lower inclinations. Whereas an aperiodic dipping behavior would correspond to a star-disk interaction, that occurs in an unstable regime. So this would be the equivalent of a stochastic star observed at lower inclinations. We also conducted a structure function analysis of the Kepler light curves in order to extract the dominant timescales of variability associated with each light curve morphology. So across our time series, we extracted all time lags from the data cadence to the duration of the monitoring, of the K2 monitoring. And for each of these timescales that we could extract from our time series, we measured the average amplitude of variability among all pairs of points in the light curves that are separated in time by that amount, by that tau. So the theoretical expectation is that when we study very short time scales, the photometric fluctuations that you observe would be mostly dominated by photometric noise until we enter the main regime, the main region of variability. So in this regime, the structure function is expected to increase in value with tau until the dominant time scale of variability is reached. Beyond this dominant time scale, the variability that you observe would simply be a reflection of the variability on shorter time scales, resulting in a flat or oscillating behavior along this maximum value of the structure function. So from our structure function analysis, we could extract two main conclusions. The first one is that for any given light curve morphology, higher mass stars, which are shown here in purple and in blue, are less variable than lower amplitudes of variability than lower mass stars, which are shown here in yellow and in red. So on one hand, this might be understood in terms of disk-related variability, which triggers more intense amplitudes of variability, and it is found most frequently among lower mass stars. But the same behavior is observed also among flatline stars. So
2 minutes, Laura. 2 minutes.
Thank you. So this suggests that the reason why higher mass stars are less variable than lower mass stars may be linked to the distinct magnetic field structure among at the surface of different stars of different mass. So higher mass stars would harbor a more complex magnetic field, which could correspond to a more uniform distribution of magnetic features at the stellar surface, yielding a lower modulation effect than on lower mass stars. And the second conclusion is that although there are some differences in the timescales of the dominant timescales of variability that we could extract from different light curves, the typical timescales of variability for all behaviors are of the order of a few days to 1 or 2 weeks, which correspond to the rotation rates for these young stars. So this would suggest that inner disk processes typically do not exhibit any large-scale structural variations over tens to hundreds of rotational cycles, although they can exhibit a more erratic variability on shorter time scales. So this is my summary. So variability monitoring provides a key tool to probe the inner disk dynamics. Young stars can exhibit a wide range of behaviors that are driven by a combination of magnetic activity, star disk interaction, and viewing geometry. For any light core morphology that we detect, lower mass stars are always more variable than higher mass stars, possibly triggered by mass-dependent magnetic field structure. Dipping behaviors are not observed among stars earlier than G, which suggests that the higher surface temperatures for more massive stars and the more chaotic magnetic fields from massive stars would prevent the formation of stable inner disk structures that would correlate with the star. And finally, the inner disk timescales of variability are typically consistent with the stellar rotational timescales. Thank you very much for your attention.
Thank you, Laura. So questions from the audience here?
Nice talk. I just wanted to ask you about the variability. Sometimes like the deeper light curves that you show were kind of constants and then a dip and then a little bit constant and then a dip. And that reminded me of the UXORI variability that is typical in some Herbig KEV stars. So, but I'm surprised that then you said that, you know, you don't find it in stars earlier than G. So what, can you elaborate on that?
So what we observed in this region, and it's confirmed by ongoing studies also in other regions, including Taurus, is that this dipping behavior is not observed. So any other category of variabilities, including Barcer, is observed across the mass spectrum, but dipping behavior disappears on spectral types earlier than G. And so we made a computation of the radius, like the minimum period over which we could detect structures correlating with the star around stars of mass higher, corresponding to spectral types higher than G, given the model temperatures and the disk temperature. And what we observed is that for higher mass stars, for stars of mass higher than G, so starting from the after F-type stars, so the minimum period, the minimum rotation period for which we could observe co-rotation of dust structures, the star, are too long compared to what we could detect here. So dust structures could not survive at disk orbits close enough to the star for us to observe this kind of behavior. And this is consistent with what was found in this study, Bodman et al. 2017. So they had also similar conclusions. So this seems to be triggered by physical conditions in the inner disk that would prevent us from observing this type of variability.
The only thing is that maybe you want to look at the UX ORI variables, which are reminiscent of that, and then you want to see how it fits into this. That
would be like not on the same time scales of variability. So you are looking only at variability on the deepening behavior that takes place on time scales of days. So then there we would look at much longer time scales.
Okay, and I think we have a question from Antonella Nata online. Antonella?
Hi, Laura. It's not really different from what Nuria has asked you, but I think that there are stars that change their pattern of variability also among the T-Tauri stars that we've been studying. You know, a typical example is AA Tau, if I'm right about that. Have you any feeling for how stable this modality of variability are? Or, you know, if one of the reasons why we, for example, we think that higher mass stars do not have any of this is because we don't see the same erratic, huge variability among T-Tauri stars because we haven't searched in the same way or with the same kind of time scale.
So we do not over the time scales covered by the K2 time series, which is around 3 months. We do not observe switches in behavior. But in the NGC 2264 campaign, which was coupled, which was combined with what's for which we obtained 2 separate Corot epochs in 2008 and 2011. We did observe that around I think 30% of the stars switched behaviors along this time span during this time lag. So they seem to be stable, at least on timescales of months, but we do expect switches in variability over timescales of years.
Okay. No more questions? One online. Well, we have time for a very quick question online.
Yeah, it's from Zhen Guo. Laura, he's asking, have you seen or predicted different variation patterns, i.e. timescales between single and binary YSOs?
So this is the next step of our work. So we do not have, we are starting now a survey to answer exactly that question. So how the presence of binary companions impact both the timescales of variability and the morphology of variability to observe. So hopefully we will have an answer to that in the near future.
Okay, thank you very much, Laura. Thank you again. Okay, and next we have a talk, another online talk by René Oudmayer from the University of Leeds on the formation and evolution of Herbig AEBE stars.
Thank you very much, Enrique. And hello, everybody. Hello. From Leeds, it almost sounds like Eurovision, isn't it? I'm afraid I couldn't be there. COVID and also teaching. The students were so happy to see some lectures in live that would be very difficult to leave. So yeah, today I'd like to talk about Herbig AEBE stars, and mainly what I'm going to talk about is the work by some of my PhD students, John Fairlamp, Karim Ababakar, Miguel Vioca, and Chumpon Wechitaneko. And as you can see from their destinations, you can see that whatever I did to them, they fled Leeds, not only the country, but also the continent. So there you go. So I'd like to give you a little bit of an overview about why I think Herbig AEBE stars are very important in understanding star formation. I'm talking about the links with T-Tauri stars because officially people think that Herbig stars are actually quite massive. Like to talk about the accretion mechanisms and actually see where the high mass star accretion differs from that from low mass stars. And I will finish by some work that we did with Gaia. So just to set the stage, these are the cartoons that we know from the different classes. And I'd say that when we talk about Herbig A-B stars, we talk about the classes that are indicated here in the graph. So basically class 2-ish, class 3-ish, where we still have a star with a disk, an accretion disk, perhaps some outflows and planet formation going on. And I couldn't believe it that the color scheme of the observations was exactly the same as that of the cartoon. But here you got a little bit of a flavor about how these Herbig AEBE stars look like at very high resolution. This is a paper from Nienke van der Marel. Okay, so and another thing, I don't think we mentioned it today yet, but Herbig AEB stars are also fantastic test beds to study planet formation. And indeed, planets have been detected around Herbig stars already. I just wanted to say this just to put it into context. I'm not going to talk about planets later on. Okay. So where are we with the Herbig stars? So here I've got an HR diagram from Villebron et al., where you can see the various evolutionary tracks. But they basically said, okay, if you've got the lower mass stars, they're fully convective. Then we move to stars that have radiative envelopes. And I think the three classes of star that you can see in this HR diagram are the low mass Tittori stars on the bottom right. Then we've got the intermediate mass Tittori stars that actually have the masses of stars that will become A and B stars, but they're still very cool. So they're more like a Tittori star. And then we've got the Herbig AEBE stars. They're intermediate masses, say masses between 2 and 10, perhaps even 20 solar masses. And the spectral types roughly from F, although it's called Herbig A star, to about B0. And let me also zoom out here because the luminosity on the vertical scale is only about 100. So on the right-hand side, I've got a more complete picture of the HR diagram and Herbig AEB stars, and you can see that they move all the way to very bright objects indeed, and very high masses. Okay, so in my simplistic view, there's three types of pre-main sequence stars. We've got the low mass Tittori stars, where we actually know that they form, that they accrete the material through this magnetospheric accretion. We can see them in the optical, which makes it very well good to study them as well. Then we have the Herbig AEBE stars. They are of intermediate masses, I just mentioned. And one thing that's really nice about them is that we can see them in the optical. And at the highest masses, we've got massive young stellar objects. And arguably, you can't even see them because they collapse so quickly that they're still obscured by the parental cloud. So in that sense, I think the Herbig AEB stars also form a bridge between the low mass and the high mass stars. Okay. And one of the things that that I'm interested in as well is like, okay, what kind of accretion do we have at the highest masses? Because as I just mentioned, we've got the magnetospheric accretion in the Tittori stars. And when I had this particular color plot on the screen and everybody was showing Lee's book, I couldn't resist. He actually has exactly the same picture all these years ago. And the only difference actually the progress in the field is that we moved from black and white into color. So well done. The question so is that why would I expect a higher mass star to have a different type of accretion? Well, we assume typically that because higher mass stars are radiative, they don't generate a magnetic field. Okay, so you would immediately expect that the accretion onto the star would be different. Now we know that about 10% of all the main sequence A stars are magnetic, and people actually found that 10% of all the Herbig AEB stars that we know are magnetic as well. So there might be something going on. It might be a fossil field, for example. But even having said that, if you go to the more massive stars, how can we get matter accreted onto these stars? Okay, and there's a couple of tests I want to show you today, and we will find that there's about a break at around 3 to 4 solar masses. And one of the things that we've been trying to do is just to look very close to the star. And as the previous speaker said, oh, we can look at variability. We use something called spectropolarimetry across the H alpha line to check that. It could be a seminar in its own right, just like let me just describe it in 1 or 2 minutes. If I've got a star surrounded by ionized material, I've got a lot of free electrons close to the star that can scatter the light from the star itself and polarize it. While the H alpha also arises from an ionized region, but it's much bigger. I need lower density. So the H alpha line would be less polarized than the continuum. And if that's the case, and if the scattering material is asymmetric on the sky, like in a disk, for example, then we can actually try to observe that effect. And the principle has first been applied already in the 70s when people didn't know what the nature of BE stars were. But now we know this is surrounded by disks, for example, and the spectropolarimetry did it. Okay, so turns out that if I would be looking at a BE star, for example, where I've got a disk reaching all the way to the stellar surface, I would have an H alpha emission here on the left-hand side, but I would find a basic depolarization across the line, as I just more or less tried to explain. However, if we're looking at T-Tauri stars, where you've dumped material onto the star via these accretion funnels, you have a completely different situation. And the a priori prediction is really that you will find a kind of a depolarization across the line, but also a flip in what we call the position angle. Basically, normally the position angle will tell you what the position angle of the disk on the sky is, but there would then be a flip across H alpha. Okay. And that's what we try to observe towards our Herbig AEBE stars. And I should first note that what I'm going to show you now might look a little bit noisy, but it takes hours and hours on 4-meter class telescopes to get these data because we need signal to noises of around 1,000. And what we found is that B-type stars, Herbig B-type stars, have this wonderful depolarization, but essentially a flat PA, position angle, while a T-Tauri star shows a flip in the position angle just as the doctor ordered. But typically all the Herbig A-type stars also show this flip, okay? I only show you 3 examples, but this already tells you something that perhaps there's a difference between the Herbig A stars and the Herbig B stars. And when we got data for almost every single object that we could look at, we found that the Herbig B stars show this basic depolarization, as I explained earlier, while the Herbig A stars really look like the T-Tauri stars with the flip. So this is an observational effect. We can explain the flips with the magnetospheric accretion, and we can explain the simple depolarizations with disks reaching all the way onto the stellar surface. Okay, so this is an observational, absolutely great difference, big difference between the Herbig A stars and the B stars, but the A stars behave like the T-Tauri stars as well. So if you want to speculate, you could even argue that, well, if the disk situation is similar to T-Tauri stars and Herbig A stars, perhaps they form like T-Tauri stars as well, and there might be magnetospheric accretion. Okay. Now then, so let's take another step and let's think about accretion rates of these Herbig stars. And we use a trick that was has been around for quite a while, of course, going all the way to 1998 with Nuria Calvert, for example, where people looked at T-Tauri stars and said, okay, the accretion shock will emit in the ultraviolet. And by measuring the ultraviolet excess, we can measure the luminosity. And if you know the mass and the radius of these objects, you might even get the accretion rate. And that's what we try to do for Herbig stars as well, based on work, the foundational work by Mucciarolo, for example, who applied it to Herbig stars. And Donju in Britain in 2011, we got spectra, X-shooter spectra of a large sample of Herbig AEBE stars, and actually found that they all have indeed an ultraviolet UV excess over and above that expected from normal stars. Okay, and then you can extrapolate this and get a value for the accretion luminosity. One of the first things that we did was just to plot the accretion luminosity as a function of the luminosity of the star, which I've got here on the horizontal axis, and the biggest symbols are the Herbig A stars that we observed, and the T-Tauri stars taken from the literature. And you can see that they more or less follow the same trend, which is in a way reassuring that the method works, okay, assuming that we have accretion going on. I'd like to take one step further and actually say, well, hang on, it would be nice if we could even look at the masses of the stars and perhaps even compare with the ages of the objects. But for that, we'd like to put all these objects into the HR diagram. And that's what Miguel Vioca did in 2018. And Chumpon Wichitanicom added some objects to the sample, derived the stellar parameters of these objects, and then derived the accretion luminosities and accretion rates. And the result is in this, this graph. What you can see is that we've got the beautiful in the HR diagram and the color-coded as a function of accretion rate. I should note this is all based still on Gaia DR2. There's some more objects and slightly and more refined parallaxes are now available with the Gaia EDR3, and we worked them out. We list the distances and the parallaxes for those objects in Guzman et al. So I mentioned accretion as a function of time, and that's something that people have been looking at a lot. And if I would just take all these objects at face value and plot the mass accretion rate as a function of the age of the objects, because I got them from the position in the HR diagram, I see a very strong correlation that the younger the object, the higher the mass accretion rate. And that's something that people always have been predicting already. But there's a big but in this graph, because I just showed you the HR diagram, and we found that actually the highest mass objects have the highest mass accretion rates, okay? And the lowest mass objects have the lowest mass accretion rate. So if I am interested in looking at the mass accretion rate as a function of time, I really want to look at the very narrow mass range in this graph, okay? And
2 minutes.
Thank you. And that turned out to be actually quite difficult. So we found a very narrow mass range. The best one we could find was between 2 and 2.5 solar masses. And we find a trend that's not mass dependent, and we find that the mass accretion rate goes with the h to the power minus 1.9 plus or minus 0.5. So it's quite a big error bar because of the problems I just outlined. But it gives you an idea, and it's actually quite an agreement with what Lee said all these years ago as well. I've got 2 minutes to, oh yeah, I've got a final thing is here. We looked at the mass accretion rate as a function of mass, and it turns out to be a break in the slope in this relationship if I look at the high mass and the low mass Herbig stars. And it's a much shallower mass dependence for the high mass stars, and the break is around 4 solar masses. There's a whole host of references that tell us that A and B stars, Herbig A and B stars, are different. And I think we pinned it down now, it's around 4 solar masses. Got now 1.5 minutes to talk about last work that we've done. It's also on the poster by Miguel Vioca. And what we wanted to do is actually to find new Herbig stars in Gaia found in a homogeneous way. Okay, because all the Herbig stars I've been talking about have been found actually serendipitously. So what we did, we made a training set containing infrared data, H-alpha data, Gaia parallaxes, found a master sample of 4 million objects in Gaia. And out of those, we found, we had a training set with 800 known pre-main sequence stars, including the Herbig stars, some known BE stars, and a random set of objects. And then we let machine learning do its thing. And 2,000 of these 4 million objects had properties that were exactly the same as that as the Herbig stars and the pre-main sequence stars that we gave it. And even if we put them in the HR diagram, they already look like they're off the main sequence a little bit, as you would expect for pre-main sequence objects. And because the parallaxes were not part of that selection, I think that was quite reassuring. But we just wanted to make sure that these are real Herbig stars and not just candidates. Even better, because if you know what the spectral type of your object is, you can correct for reddening. So we went observing. At time with 3 different telescopes, looked at 160 objects. Near typical spectra, I've got here a spectrum in the blue. We find that an object is a B star. We find in the red that these objects, this is also the blue, this is H beta emission. And to make a very long story short, out of the 145 Herbig candidates that we did not know the spectral type of before, 120 are either an A star or a B star and have emission, which is quite amazing actually when you think about this, because the machine learning didn't know anything about spectral types. And all the 14 out of 14 BE stars turned out to be really B stars with emission. So that was actually quite reassuring. These data are now being investigated. We have been able to place them in the H diagram, and even we have been able to work out some accretion rates for a couple of them. So this is quite hot off the press. Turns out that our new set of data is behaving like the old set, which is reassuring in the sense that although the Herbig stars that I was talking about in the beginning are a little bit heterogeneous, the results still stand. Okay, so that was a poster in 1 minute and 15 seconds. So let me have some takeaway conclusions for you. So I hope I convinced you that the Herbig AEBE stars really help us pinning down the differences between the high mass and the low mass stars to actually form a bridge between the two. Based on the spectropolarimetry and the mass accretion rate dependencies, I hope that from larger samples I've made clear to you that there is indeed a difference, and that we find it in the Herbig star AEBE range around the 4 solar mass mark. In white, I discussed the new samples of stars, and based on time, I actually did not show any data talking about infrared variability, but we do find quite some oxidars in the data as well. If you want to hear more about it, I'm happy to talk about this. So the final question is, what is it that is doing the accretion onto the star for the higher mass objects? And yeah, we have to invoke something like a boundary layer, because if a disk that is Keplerian rotating is reaching onto the star, then probably the material needs to lose angular momentum, hence velocity, and then emit a radiation, probably in the ultraviolet as well. Okay, that's what I wanted to share with you today. Thank you for your attention.
Thank you, Ray. Okay, we have time for 1 or maybe 2 questions. Not here from the audience. I can see. Oh, Nuria.
Just to understand, in this training set that you have, or your results, of the stars that are more than 3-4 solar masses, the real early B stars, how many are BE? And how many are Herbigs?
Yeah, okay, so I of course skipped quite a lot of stories. So we had objects that were flagged to be, say, 90% chance of probable to be a Herbig star. And we had objects that were 90% chance to be a BE star, because the machine learning actually found they were different, okay? If I look in the HR diagram and I spectrally type these 120 Herbig AEBE candidates, so I can actually get the extinction correction, then all the black dots in this HR diagram are the new ones, while the colored ones are were the known objects. My guess is that I think around this bit, I'm looking at BE stars, sorry, Herbig BE stars. But these are the Herbig BE candidates as opposed to the BE candidates. I hope that clarifies it a little bit.
Okay, thank you. No more questions in the audience? No? Ah, over there. Mm-hmm.
Hello. So I'm a PhD student at UCD. I'm working also on Herbig AEBE stars, and specifically on spectroscopy. And this break at 3 to 4 solar masses that you saw in the spectropolarimetry. Do you expect that there's a change in accretion mode at that break? You might have told it, but I might have missed it.
No, that's fine. So I would argue that because the Herbig A stars look like the Titori stars, because we can explain the spectropolarimetric signatures actually with hotspots on the star, like for the Titori stars, it can be argued. And actually, I only said that I wanted to speculate, so that's why you probably missed it. But I could even argue that Herbig A stars behave like Titori stars and accrete material via magnetospheric accretion. And the B stars, they really look like a different thing. And also based on the evidence of the spectropolarimetry, if there's disks going all the way into the star, then the only way of accretion I can think of, at least, is kind of a boundary layer accretion. So a very long answer to your question, which basically could have been, yes, I think there's a different mode of accretion.
Okay, thank you very much.
Thank you for asking the question and me helping to clarify it.
Okay, we thank Renee again and all the speakers of this pre-coffee session.
Enjoy.
And we reconvene at 4:30. Okay, welcome to the second half of the, I'm hearing myself. Okay, to the second half of the IMF session. And now we have another online talk, right, by Cesar Briceño from the Cerro Tololo Inter-American Observatory about observational studies of the IMF, from my work with Lee Hartman to the present. So take it on, Cesar.
Okay, thank you, Enrique. I'm very happy to be here. It's a privilege, and I am very thankful to the organizers for having invited me to talk today. I'm only sorry I can't be there in person, but well, maybe some future time. So today I'm going to be talking mostly a kind of historic journey of observational studies of the young stellar populations and the IMF based on the work that I've been doing with Lee for many, many years now. So the ensemble properties of young stellar populations really are key to learn a lot of the things that we want to know about the star formation process in our galaxy. And in particular, in each star forming region that we look at, we are interested in finding about population-wide properties like the mean age of the population, the initial mass function, the secretion fraction, or the multiplicity, and so on. Now, going to the IMF, as we know, it's basically the distribution of masses in a given stellar population. Salpeter, in his seminal 1955 paper, called it the regional mass function. And we already seen several times, like in Patrick Hannibal's talk and so on, that even though, you know, it's a good fit, the power law, originally defined by Salpeter, is a mostly good fit down to about a couple of solar masses. There's a turnover of lower masses, so there have been other formulations as a, you know, multiple power law, a lot normal, and so on. So what do we do to derive actually an actual IMF? Well, I mean, in the solar neighborhood, in the field, you know, just star counts, and we assume a given main luminosity, main sequence mass luminosity relationship. We assume a birth rate or star formation history, and so on. The star forming regions, we actually look at, you know, we have to map the population, of course, also count stars. And then we try and look at the location of the stars in the HR diagram and compare those with the theoretical premium sequence evolutionary track, so we can derive masses. And then for the thing is, that looks pretty straightforward. Other than that implies a lot of things, and one is, of course, having a complete census of the population, knowing the ages so that we're not mixing pears and apples. The spatial distribution comes into place also. Are we looking at a cluster population or more spread out? How big do we want to average things out? Do we know the distances? Now that's being solved, of course, with Gaia, but what about differential reddening, mass aggregation? And actually, most derivations of the IMF end up being the system IMF, really, because, you know, there is there's still a lot of unresolved binaries, multiples, which complicate the picture. We're not there yet. In some regions we are, but then we're not there yet in determining single star IMFs, because we simply there's still a lot of work to do in multiplicity and in many star forming regions. So as with most every other aspect of star formation, Lee has worked extensively on characterizing stellar population in star forming regions, especially in the solar neighborhood, and studies of IMF. I've had the privilege of working with him for the almost 3 decades now, since I started as my first forages with him as an undergrad student, and then with him as my PhD advisor at CFA. And as I said, I'm going to take this kind of historic journey of the things that we've done, focusing on a few nearby star forming regions that we worked heavily on, mostly Taurus and Orion. So what was the state of what we knew in the early 90s when I was starting to work with Lee? Well, for starters, we were just getting to map the full premium sequence population in nearby complexes like Taurus, Scosen, Orion, Lupus. This is just from our 1998 paper, and showing the spatial distribution of premium sequence stars, low mass premium sequence stars, which is pretty much everything there is in Taurus, overplotted against the 12CO contours of the molecular cloud. And that was pretty much it. I mean, we're talking about some 60-odd stars or so. And actually very few low mass stars, by that mean later spectral types later than M3 and 4 were really known at all in Taurus. The nearest young moving groups were certainly not being discovered. T-Tauri stars with ages more than just a few million years were basically unknown. You have to realize that it was just nearly in 2000 that Joel Kastner et al. And his collaborators proposed that there was the handful of young stars that have been found in the rough area vicinity of the TW Hydra T-Tauri star, which was known from the mid 80s. And that was actually a nearby young stellar group. And that was, interesting also because it was unrelated to any dark cloud that we knew about. And that color magnitude diagram, and the plot on the right is the equivalent width of lithium of the then known TW Hydra members as a function of color or as a proxy for effective temperature, showing that these objects had lithium abundances that were effectively way above the envelope of young main sequence stars like the Pleiades. So they would basically have undepleted lithium, and therefore for late type stars, that was a signature that they were really young. As we have seen, the magnetospheric accretion model had gained hold in the community by this time, but accretion rates were not really well known. There was a huge spread and so on. Brown dwarfs were just being discovered. This is the image of the first one, Gliese 229b. The Rovolo group had just discovered Tete 1 so about the same time. And there were still very few determinations of the initial mass function in the nearest star forming regions. Actually, we pretty much didn't know what was going on, certainly not at the substellar limit. I mean, that was mostly virgin territory, just waiting to be explored at that time. These were, as I said, just some of the aspects of premium sequence stellar populations that needed study. If we really wanted to move forward understanding the IMF and star formation in the galaxy at that time. And of course, this was already apparent to Lee, and he already realized that this was a way we had to move forward as other people did. And he embarked with students like me and others, and his many collaborators, and tackled this set of issues. So let's start by the mapping of young stellar population in nearby regions. So, as I said, we need the census. So we need to find the stars first if we want to derive any IMF or anything else. So, of course, we looked to Taurus, one of the first. For starters, this was the region that Lee with Scott Kenning had just studied extensively at the time, and just published the state-of-the-art summary of all the knowledge of premium sequence stars, T-Tauri stars in Taurus in Kenning-Harman 95. Still, there were few premium sequence stars with lower masses now at that time. Total population, as I mentioned before, was some 70, 68, 70 stars. This is exactly the color magnitude diagram for everything known in the time of Kenning-Harman. And you can see that down here in the M5 region, that's pretty much where everything cut off. I mean, there was one star known with M5.5, and that was it. And here is the 0.1 solar mass evolutionary tract. These are tracks from, I think, Dantona and Mesitelli tracks, and here in dotted lines are the isochrones. And you can see that, pretty much everything is contained between about 0.8 solar masses and 0.3 or so. So at that time, we had access to the 1 meter Schmidt telescope in Venezuela, and also to the MMT at Smithsonian to do confirmation follow-up spectroscopy. So we embarked on a large-scale photographic survey, objective prism survey of Taurus, and later complemented that with X-ray observations with the ROSA X-ray satellite that I believe Tyler already mentioned before. And this basically produced these two papers. The first result of the Schmidt survey and a large-scale objective prism survey and X-ray survey of Taurus Orion. And I can summarize the results pretty much in this plot where where I show, and with the large circles, both solid and dashed lines are the objective prism plates, the first ones and the later ones. Everything projected on top of the CO contours, 12 CO contours of the outlining the Taurus clouds. And some of the groups of the Taurus groups are indicated here with the LIMS dark cloud designation, like L1544. And so we cover about 60 square degrees. We increased the known sample of later type T-Tauri stars at that time by about 50%. That we're talking only about 14 stars. And we basically revealed a new group in L1544 where only one T-Tauri star was known before. So, we were making progress in finding out, revealing the premium sequence population. Then we focused, we turned our attention to OB associations like Orion OB1 and Cepheus OB2, because as much as Taurus was a reference star forming region and highly studied and very interesting, it was clear by that time that most stars actually form in OB associations and not in the quiescent environment of Taurus and other T associations. So if we wanted to really understand the average environment of star formation in the galaxy, maybe the average environment where the sun formed, we really wanted to look at other regions with more massive, both massive and low mass star formation. Orion Cepheus are relatively nearby massive star formations. They were nice in the sense that they span populations from ages, just 1 million years to about 10 million years, just based on the study of the high mass stars and the B stars, and they're kind of very uncertain, but off main sequence evolution. But basically, almost nothing was known about the T-Tauri star population in this region, especially if you go away from the cloud. I mean, clearly, there's OB associations. There was a lot of study of the on-cloud population. The Orion Nebula cluster was, well known. There were tons of T-Tauri stars there in the L1641 cloud and so on. But there were supposed to be stars out there beyond the molecular clouds, where there were still OB stars, and little was known about that. So we started the CEDA variability survey of Orion. Many papers were published. These are probably the four main ones from about 2001 till recently. So we've been working for this, as you can see, for almost 20 years. And the summary is basically in this slide, showing the spatial distribution of all the T-Tauri stars in the CEDA variability survey, projected against the isocontours of the molecular clouds, and showing roughly the extent of the OB associations in Orion. OB1b is roughly this circle that encompasses the three Orion belt stars. Everything out here is what people call the 1b-A association, and down here we have the Orion Nebula cloud embedded in the Orion A cloud. We will see we will be told later during the meeting, of course, that this whole view has changed with Gaia, and if we now try to look at things from a kinematic point of view, the way we divide up the Orion, the regions like Orion, like Marina will probably talk, will be very different. But this is, just based on the projected distribution of the sky. And so we found about 2,000 T-Tauri stars that were not only have photometry, but were spectroscopically confirmed. They had spectral types, they had lithium measurements, and many of them have, a subset of them had radio velocities and so on. They had measurements of H-alpha, so we knew which ones were classical T-Tauri stars, which one were weak-line T-Tauri stars. And not only that, but we also identified in this older region some clusters of somewhat older T-Tauri stars. In Cepheus, we did a similar work with Aurora Cecilia and other students and collaborators of Lee. Basically, two regions, Trumpet 37 and NGC 7160. Again, starting to reveal the first sets of stars in somewhat older populations in OB associations. So the second thing is, where were the older T-Tauri stars? Those that were supposed to be out there if there was a continuing process of star formation in the solar neighborhood, if molecular clouds had dynamical timescales of order tens or so million years, where were those T-Tauri stars that formed generations before? Not necessarily the ones that were just 1 to 3 million years, the ones that you saw projected on the cloud. This was the post-T-Tauri star problem posed by Herbig. And in that sense, of course, was something that Lee was very keen in addressing, and we did that in this paper in '97. That came out basically after the Rosa Sky survey had identified hundreds of T-Tauri star candidate stars from as X-ray strong sources projected in and around the regions of wide areas nearby molecular clouds, and thought, oh, these are the T-Tauri stars we're looking for. The problem with that view is that G and K main sequence, young main sequence dwarfs up to about ages of about 100 million years are also very active in X-rays. So, and because they're foreground to most of these clouds, they tend to be picked up by these large scale X-ray surveys that were not that deep anyway. And so we found that they were biased towards these young main sequence stars. And even though like here, you can see in red, the X-ray sources, they certainly cluster, of course, towards the Orion Nebula cluster, NGC 2024, and the known young places in Orion. There's a lot of them outside here, but does that mean that these guys out here were also T-Tauri stars? Turned that out that they were not, and they were just young active field G and K dwarfs. Of course, Lee, has been one of the foremost authorities in discretions, and one of the papers I had the pleasure of collaborating with him was the disaccretion rates for T-Tauri stars, on which we managed to get 5% spectrophotometry of a whole sample of T-Tauri stars in Taurus on amazing, wonderful sky conditions at Mount Hopkins that we probably never saw again. I know. And at that time, the main result was, well, I mean, accretion rates are probably mostly lower than they were thought. On average, maybe an order of magnitude less that people thought. And also a very important thing is that, in that paper, it was proposed to use the U-band excess luminosity to estimate mass accretion rate, and that weak-line T-Tauri stars should be used as templates instead of main sequence stars, because their photospheric colors are redder compared to the main sequence star of the same spectral type. Of course, a lot of this is all has been all put in the these wonderful and reference textbook on accretion, which I had to put there. Then the other thing is, what is the spectral type of a pre-main sequence brown dwarf? I mean, what was the substellar limit like at young ages? That was largely unknown, and with Lee, and Kevin Luhman and George Rickey, we did this little paper on trying to determine whether this guy, which was an M6 pre-main sequence star in Taurus, was actually a young brown dwarf. And so at that time, basically from this and other work by a lot of other people, it was determined that the substellar boundary at ages of a few million years turned out to be somewhere between M6 and M7 spectral type. And finally, what was the IMF of nearby star forming regions? So of course, we started with Taurus, as I said before. We did a bunch of papers there. A lot of that building on the comprehensive review by Kenyon and Harman in '95. So we searched for low mass pre-main sequence stars in Taurus. That was the emphasis. Look at the lowest stellar masses, and if possible, go down to the substellar limit. And that work was largely with Lee and Kevin Luhman, John Stauffer, and others. Here is what we started with. This is the mass distribution from Kenyon and Harman. There are figure 17. The solid histograms are the actual measure masses. Based on D'Antona Massitelli 94 models using either convection, Canuto Massitelli convection and Alexander opacities, or mixing length theory and Alexander opacities, depending on what you assume. You got somewhat different results as you can see here. And for comparison, in the black line histogram is a Miller-Scalo IMF. So, as I said, we will try to go deeper. So with Kevin Luhman and Lee, we surveyed an area of about, little less than 10 square degrees, going very deep photometrically with a photometric study, and then trying to obtain confirmation spectroscopy. And this is basically the result of what we got there. We put things on the HR diagram and got things down to less than the substellar limit. So a number of substellar candidates in torus, candidates for being young brown dwarfs for the first time. And to build this mass function, here is the vertical line, is the completeness limit. And you could see already that, you know, we were starting to fill the lower mass bins. Similarly, we also embarked on studies of the IMF in Orion with my former student Juan Jose Downs, did much of this work, and other collaborators at CIDA in Venezuela at that time. The result was that we looked at the newly discovered 25 Ori aggregate from the CIDA variability survey, and we could, showing here is the result of that of our work in that cluster in black, in the black dot, sorry. And depending on what you assume, you could compare with a Krupa style broken power law with the Chabrier log normal IMF, and things seem to be mostly consistent.
5 minutes.
Okay, thanks. And here, still in this shaded region, there was a lot of uncertainty in the IMF, in the brown dwarf region, of course, because the numbers were low, but we were starting to get down there. So from all this work, what do we do now? Well, censuses of star-forming regions have certainly improved greatly. Gaia has been a game changer, especially in the optical for low extinction regions. Spitzer and Vista have made enormous contributions for embedded populations. And you can see it here. I mean, Taurus has gone from just a 60 some odd members now to over 500 in this plot from Espling Lumen 2019. In Orion, OB1, as I said, we've got over 2,000 members, about nearly 350 just in this 10-ish million-year-old aggregates. Upper SCO is no different. This is just work from to compare from Lumen and Espling. Upper Scorpius is outlined here in blue, and that contains confirmed over 1,000 spectroscopically confirmed members with proper motions and parallaxes and so on. Not only that, the populations have been mapped, but extensive photometry and spectroscopy coupled with Gaia has allowed us to characterize these stellar populations, derive things like disk fractions. Here to the left, for Taurus, down to below the substellar limit. Here on the right. Here from our work in Orion, especially on the right, is the evolution of the disk fraction in red, and of the accretor fraction in red and the disk fraction in gray for the different age populations across the whole Orion region. And that's a nice thing, Orion, you get the sequence of ages and you can do this kind of games and map things out in this way. Look at the time evolution. Many 10 to 20 million year old populations are now known in the solar neighborhood. And this is just adapted from a table in Torres et al. With Gaia distances and ages from Ujwal et al. 2020. And you see there's a whole number of groups from ages 5 to 30 and 40 million years, nearly 40 million years and so on, within, you know, less than 300, 400 parsecs.
2 minutes.
Yes, thanks. And finally, the IMF has been extensively studied not only Taurus, Orion, but other regions like IC 348 and so on. Down into the substellar limit, we know now very young brown dwarfs down to M9, for example, as we can see here in the spectra. The IMF, I mean, this is this distribution of spectral types, which is not exactly the IMF, but similar observational parameter, and they're very similar from one region to another. And as seen here in this plot we've seen before from the review by Bastian, the IMF is actually across different star forming regions in our solar neighborhood, and even in other stellar system much older in the galaxy. They all seem to be quite the same, very similar. So end up saying, is the IMF universal? Does it really vary with environment? What about, does it depend on gas and star density, metallicity, stellar multiplicity? What about the initial conditions in the clouds? If so, why is it that so many different regions exhibit similar IMFs? I mean, how can a process so complex as star formation that involves a myriad different variables end up always producing about the same result? In that sense, is it even correct to assume universality? Maybe when we do that, we are somehow hampering ourselves in not choosing the appropriate path towards testing for actual variations. And actually, recent evidence suggests that the IMF may be different in systems beyond the Milky Way, like massive early type galaxies, maybe because of different metallicities or star forming regions, etc. And certainly much work remains to be done in things like multiplicity to go from the system IMF to the single star IMF. So I think I'll stop there. More than a review on IMF, I just wanted to take you along this long journey and tell a little bit the tale of where we started and how we've got here from this perspective working with Lee. I'm really, I can't say how happy I am about having been able to share this world with him and many other people along these past years. Thank you.
Thank you, Cesar. Let's see, any questions from the local audience? Well, maybe I just have one short comment, Cesar. It's a little bit off the topic because it refers mostly to ages. But I wanted to get your point of view about the reality of a certain members of the populations that have older ages. And in the simulations, I agree that many of them may be like field stars and so on. But is there like a significant fraction of, or is minor but significant fraction of older stars in the clusters? That's what we do see in the simulations and in some modeling for the evolution of the clouds and the clusters.
Yes. Do you mean like even if the cluster mean age is?
No, I mean like the histogram.
If you have the real outliers.
Yeah, I mean like in the real age histogram of the cluster, there seems to always be a small tail of older objects, like a few million mega-year-old objects, or maybe up to 5, 10. And we do observe that also in the simulation. So, but what is the observational point of view? Are all those ruled out as field objects, or are some of them truly older, a few older objects in the clusters?
Well, I mean, I think that we have found always there are a few oddballs here and there. Not all of them can be dismissed as field stars. There are a few, I don't remember off the top of my head, but there are a few well-known specific samples of, much older stars that even are still accreting, are known to still be accreting at ages where there's not supposed to be doing so. So yes, I think there may be a very small tail, and I really don't have a good answer as why you would expect to have these. I mean, maybe you do from the simulations, you understand better why you would have these few outliers. But usually, when you have them, they're only a small number, just a handful, a few. So it's very difficult to even be completely sure that they belong to the cluster population. Even then, some of them do, even after you take into account proper motion, parallax, radial velocities, everything that you can think of, everything seems consistent with cluster membership. So, and that's really hard to explain.
Yeah. In the simulations, we do see, because the star formation rate accelerates. At the beginning, it's very low. So you have a few, just a few stars that are formed early. And as it tapes, as it picks up, then you have like a burst of star formation in the last couple of million years. And that's where most of the stars form. But at the beginning, there's just a few stars formed from when the cloud was younger and not with so many density peaks.
Okay.
Lee or Tom Ray.
No, I just thank you very much, Cesar, for an excellent talk. I just want to ask you a little bit about the post-T-Tauri stars that are being discovered in the past couple of years. I know they're around 10, 20 million years old and so forth, but I'm just curious whether there's any evidence for the start of the emergence of anything like a debris disk around them. I mean, an old debris disks are usually older, but one would imagine with such a big sample, you might find some evidence.
Well, I would say that these clusters down here at ages of 10 to 15 million years are, these guys are all effectively post-T-Tauri stars in the sense that, they are more evolved. Basically, and you can see that the disk fraction and the accretion fraction here is, even though it's not really zero, it's very, very small. I mean, only about 5% of the stars at these ages are still accreting. So that means that you don't have a lot of stars with disk, but you still have a few. I mean, certainly you have debris disk, and you even still have like 1, 2 T-Tauri stars in a population of about some 50 stars, or we're talking about 5 stars in 100 are still classical T-Tauri stars by the standard classification. So yeah, I mean, even then, now if you go at 40 million years, 50, then you don't expect to find them.
Quick comment.
Just a comment, it depends a lot on the spectral type. The earlier type tend to have more debris disk, just detection limits. And then when you get to the lower type stars, lower type stars like this, then the primordial disk, the remaining primordial disks are the one that you observe. Not because there aren't debris disks, it's just sensitivity limits.
Yeah, exactly.
B and BF, yeah, sorry.
Okay, I think we need to move on. So thank you again, Cesar.
Thank you.
And the next talk is local. We have Tomás Noni from the Instituto de Radioastronomía and Astrofísica at UNAM. He's going to be talking about an overview of the ALMA IMF, the ALMA large program investigating the origin of stellar masses.
Okay, thanks. So to continue on the IMF and its origin, I will give an overview of the ALMA IMF large program and introduce some of its first results. And before I start, just a word to tell you that the ALMA IMF consortium now involved about 80 members in 11 countries, and some of them are present in the audience or online. So, do we have a universal IMF determined by the CMF? Actually, this was the paradigm widely accepted in the community until recently. The IMF, the form of the IMF would be directly related to the form of the CMF, the mass distribution of cores, and cores would be the direct mass reservoir of stars. However, now we have many reasons to doubt, to question this paradigm of a direct relation between the CMF and the IMF. First, some observations suggest variation in the IMF and found top-heavy IMF, especially in young massive clusters close to the galactic center. Secondly, these relations relies on several fragile hypotheses. When we tell there is a direct relation between the CMF and the IMF, we are making several assumptions that have been challenged over the years. For instance, the assumption that the core is a unique mass reservoir available to form the star, or that there is a constant gas to star mass conversion. And a third point, there are observational limits in the measurements of the CMF. And I will just come a little longer on the third point. To understand, we need to make a little of history of CMF. And over the past 2 decades, study of core mass function were made with ground-based telescope, with the Herschel Spatial Telescope, and as well with near extension, with near-infrared extension surveys. And they indeed found, in relatively good agreement, CMF following salpeter's slope. However, most of these studies were studies toward low mass star-forming region, and here Orion is more an exception than the rule, and mostly limited to, let's say, 10 solar massive cores. And so low mass star-forming region, and as well rather local star-forming region, starting from the Gould Belt clouds here, and later the Hobbies clouds have extended a little our scope up to 3 kiloparsec, but we are not investigating regions typical of the main mode of star formation in the galaxy. And to go further, we need interferometry to achieve a sufficient angular resolution. And ALMA has been an important improvement in our field. With ALMA, we have been able to obtain image at 5.5 kiloparsecs towards the W43mm1 ridge. And using 1.3 millimeter continuum map, we found a CMF with a flatter slope compared to the canonical salpeter value. And also important, up to 100 solar massive cores. So here is where we stand now. We do see top-heavy CMF in various protoclusters, from observations of single protocluster as our study and others, but also from studies combining cores in different regions. So how can we understand this? First, if we assume a constant core to star efficiency, we would get atypical IMF, we get top-heavy IMF, as has been observed in some regions. The alternative is that we need an evolution of the CMF if you want to recover salpeter slopes. And we can think of new episode of filament and core formation or subfragmentations to make the CMF steeper. But on the other hand, we can also expect that if cores continue growing in mass, the CMF will become flatter. And to address these questions and understand it, as observers, we need to both explore different environments in the galaxy and look for temporal variations of the CMF. And to do so in a homogeneous way, a large program is a key, and a large program with ALMA especially. So ALMA IMF is a cycle 5 project observed in 2017-2018. 15 clouds have been selected among the most massive protocluster in the Atlas-Gal PUMS catalog. And we have observations in 2 bands, band 6 at 1.3 millimeter and band 3 at 3 millimeter. We have observations of both lines such as CO, SIO, N2H+, and also spectral windows dedicated to continuum study. Regarding the spatial setup, the strategy was to build large mosaics in order to image not only the center of the region, but also their surroundings. And we have also tried to have a homogeneous spatial resolution around 2000 AU, using both the 12-meter and 7-meter array. The 2 first papers presenting ALMA IMF, the overview paper by Frédéric Mott and the presentation of the continuum data by Adam Ginsburg, will both come out soon. And you will hear more detail about the data reduction process in the presentation by Nicole Cunningham just after. In order to achieve this similar physical resolution, we applied a distance filter to the clouds between 2 and 5.5 kiloparsec. And you can see here the green circles representing ALMA IMF clouds. And these clouds have been classified in 3 categories using both the 1 to 3 millimeter flux ratio and free emission. And from young to intermediate and evolved, you see here an example of each category with these 3 color images. So in red, you have the 1.3 millimeter continuum emission in thermal dust. In blue, it's the H41 alpha line tracing free emission, while at 3 millimeter, we have contribution of both thermal dust and free emission. I will now move to the presentation of the first detailed study using ALMA IMF data towards the W43MM2 and MM3 region. So it's also a dense ridge in the W43 region. So a ridge meaning that it's a dense and cold region, and as you can see here with these air shell images. So this region is composed of 2 main parts. MM2 is classified as young, while MM3 is classified as intermediate. And you can see this blue bubble marking the location of an ultra-compact H2 region. And you now have the 1.3 millimeter continuum image of the combined mosaics with the cores that have been extracted with the GetSF algorithm. In total, we found about 2,000 cores over the entire region using a core extraction strategy that will again be present into more detail by Nicole. And using this large core population, we can build a core mass function. And again, we found that the core mass function toward MM2 and MM3 is top heavy with a slope of minus 0.94 to be compared to minus 1.35. When we look at the subregion scales, we found that there is a main contributor to this excess of high mass cores, and it is the region W43MM2. And this suggests that there is a burst of star formation occurring in these subregions. To investigate the origin of this burst, we looked at fragmentation, but unfortunately we don't have access to higher angular resolutions observations. Therefore, we can only test different models of fragmentation. And there you have in blue the same global CMF as before, while in yellow and gray are different fragmentation model based on the fractal hierarchical cascade of Benjamin Thomasson. And there, this fractal index of 1.4 means that our 2000 AU cores give 2 fragments at 500 AU scale. And you see that using this model of fragmentation and a constant efficiency, it's not sufficient to change significantly the slope of the fragment mass function. And on the other end, if we keep the same fragmentation model, but use an efficiency proportional to the mass, then the slope of the fragment mass function can become much flatter. Another direction to investigate the origin of this top-heavy core mass function is to identify protostellar core. You see now in grayscale the same continuum image as before, and overlap are the blue and red contours associated to the blue and red shifted emission of the CO221 line. In green are the cores associated to this outflow. And using the CO line, I found 51 cores associated to CO outflows that we can qualify as protostellar. And now that we have protostellar core, we can separate them from the prestellar core. And we found here that the CMF of prestellar cores only gets consistent with Salpeter slopes, while in contrast, the CMF of protostellar cores is even flatter. However, there is an important thing to notice here, is that on the left panel, we are limited to cores below 15 solar masses. There is no high mass prestellar core in MM2 and MM3, and all the high mass core are protostellar. And this may indicate that the burst of star formation preferentially feeds protostellar core. And finally, what can we tell about models? So here is another proposition of classification of the model that have been discussed today, either between core fed and or they can be clump fed, depending on the size of the mass reservoir. And I think that clump fed models with accretion on larger scales, allowing star formation to vary with core mass or core density, could predict more easily our result, which is a top-heavy protostellar CMF and possibly also the top-heavy IMF. So in conclusion, I hope I convince you that with ALMA IMF, we have a wealth of data to investigate star formation in a more typical but yet extreme region of the galaxy. We have 15 high mass protoclusters, and the 2 first articles and the continuum data release are incoming, so stay tuned for more results. I will also present results on W43 MM2 MM3, showing an excess of high mass core, which could be due to a local burst of star formation, a burst which seems to evolve mostly protostellar core, and the first CMF articles are also incoming. And if you want to hear more about this, Yuan Puto is in the assistant, so he will be happy to present it. And finally, you will hear more about lines later, but we are also putting lots of effort in it, and we have also different ideas to study the variations of the CMF. Thank you.
Thank you, Thomas. Any questions from the local audience? Lee?
So I wanted to comment that there's another way of reconciling these different slopes between saltpeter and -1 effectively. And in the stuff that Javier and I have done, where you have something like a Bondi-Hoyle accretion process, but you have to fragment first, as Patrick was talking about. And so if you have these fragments and then you accrete onto them, asymptotically, you can get to -1. But if you don't grow the mass far enough from that initial fragmentation mass, you'll get a slightly steeper slope. So, you know, that's another way of just using the same physics, but just saying it's you know, whether it's an asymptotic limit, and you might get that in the massive clusters where you have lots and lots of gas and you can grow to the higher masses.
Yeah, so as I said, we have tested different models of fragmentation. It's a bit difficult to know which one could the more fits to our observations, but yes, indeed, this one is a possibility. We have also tested gene fragmentation, but it was not the most efficient model. So yeah,
Fragmentation is a much lower mass.
Yeah. The gene fragments are far too small to be. It's not very realistic.
A question over there.
In order to derive masses for this course, right, you have to know the distance. And kinematic distances are quite good, but not very precise. The best estimate can be obtained by mesoparallaxes. So how many of those regions which you observe have mesoparallaxes actually?
Oh, that's a good question. I don't know it by heart. Probably, I think at least some regions in our sample have major distances, but tens, I think. But yeah, not all of them, but some yeah, a fraction.
Okay, we have a question here in the audience.
Thank you for the talk. Very interesting results.
So can you remove your mask, please?
Okay.
Thank
you.
So
Very interesting result. I'm wondering why the protostellar core CMF the slope is closer to the IMF, and the so the pre-stellar core slope looks similar to the IMF, but the protostellar ones is flatter. So if we expect the CMF evolve to IMF, we should expect the opposite. So what is that?
Yeah, actually, we may have different variations in the two directions. Here it's just new, so but what I think is that if during the accretion process at the protostellar stage, cores can get more massive, and then the CMF slopes will evolve like this. But on the other hand, we can also have evolution in the other direction, and it's very preliminary. But when we compare the CMF in different regions, we have a trend of different slopes between evolved and young regions. So there could be variation in both directions. But of course, we need to study more to understand this.
Okay, and we have a question on, written on the Slack, maybe?
Yeah, it's actually come through Zoom from Joe Alves, and he asks, well, stating that he's glad he's not on this side of the question, he states, how is a core exactly defined?
Sorry, how?
How is a core defined exactly?
Yeah, what is the definition of a core?
So, yeah. I can tell you more about the core extraction strategy, but maybe it's not the exact for us. The core is just an over-density that we see at one particular scale in our maps, and if we look at higher angular resolution, we may see these core fragments into several. So for us, it's more a way to measure the mass reservoir at a certain scale in an homogeneous way over the map. We have the same strategy to extract core in all over the place, and like this we can see how the mass change from. I don't know if it was the answer, but otherwise we have good algorithms to extract core, and also a little complicated. They are really efficient to deal with complex maps as interferometer maps.
Okay, well, I think we thank Thomas again. Thank you. And then we have the last talk of the afternoon, but don't go away after that. We have a video of the poster presentations. So, but first we have Nicole Cunningham from IPAG at the University of Grenoble. She's going to be also talking about the ALMA IMF program, characterizing the dense core population towards 15 massive protoclusters.
Hi, everyone. So I'm the last talk of the day before we, I guess, get to go off and sample the Guinness. But well, thank you for having me. It's nice to be finally in person in a meeting. So it's been a nice meeting so far. So I'm going to follow on from the nice talk that Thomas gave. Going more, so he gave a nice introduction to why we're doing the ALMA IMF Lodge program. And so I'm going to go just a little bit more showing you what's in the ALMA IMF Lodge program and the products that we're starting to get. And so this is, so yeah, I'm at IPAG working on the ALMA IMF with the EcoGal project as well. And so this is our overview of the sample. So I don't know if I have this, or maybe I should use the pointer. So these are 3 color images of red is MIPS 24 micron, the green is the GLIMPS 8 micron, blue is GLIMPS 3.6 micron. And these are basically the sample of all of the 15 ALMA IMF protoclusters that we have, with the white contours showing the 870 micron emission. And so the key point here is we're really sampling a range of environments, a range of evolutionary regions across the galaxy, and going to the densest, most massive points, looking at taking the mass from the 870 micron emission. And so just to highlight again the fields that we're looking at, so we have the 15 protoclusters that Thomas mentioned that we're separating into evolution. So we have from infrared quiet to infrared bright, and we're mapping a large mosaic region. So it's probably easier if we zoom in to 2 of the more extreme environments, so W51 main and W43 main. So you can see in the green contour here, we have the 3 millimeter ALMA mosaic that we're doing, and then the 1.3 millimeter mosaic regions. And if we look at W51 main, you know, we're more infrared bright, we're in the more high mass regime. So we're really probing, you know, more evolved regions compared to then W43 MM1, which is more infrared dark. So we're really probing this range of evolutionary environments and different environments across our galaxy in a homogeneous way. So that was one of the main goals of ALMA IMF, was to really do this in a homogeneous manner. And so just going on to the data side, so Thomas mentioned that we have you know, more than 70 members, and one of the big things behind this is the data reduction effort. So I just really want to highlight the data reduction team, because there's a lot of work in the background to get a large program of ALMA out there. So it's been a lot of effort, and it's still ongoing. But what we have right now is the continuum data is ready. And so that paper is now accepted, submitted by Adam Ginsberg. And so with this large data set to provide the legacy products, what we really wanted to do from the beginning is develop an automated pipeline. So we really have, this is all available. Everything we're doing to the data is available on GitHub. And we're combining all the array configurations, and we're also applying phase self-cal to the data. So here is an example of G10. And you can see on the left-hand side that pre-self-cal and then post-self-cal, we're really improving the data. I mean, the image quality is significantly improved from the products we're getting to an order of, you know, a factor of 5 in some cases. And so the data we will be delivering in the coming months, when that paper comes out in the near future, is 12 meter only, what we're calling cleanest and best sensitivity. So there is a lot of, on the website here, we have a lot of nice images already of the data. And just to highlight really the the diversity and the richness of this data set. Here is some of the 1.3 millimeter continuum maps of several of the regions. So the rest of the fields, if you want to go on the website, you can have a look at those. But we really have this incredible data set. And now we're looking to then extract the cause from that and look at the CMFs that Thomas was showing. So we have two types of the continuum data, the cleanest, which is as much of the line emission as we can get rid of from the bright regions. And so that's, in some cases, if we have a line bright region, we're losing, we can lose up to half the bandwidth. So then we are also going to produce, or we have produced what we're calling best sensitivity or B-sense data. So this is basically all of the bandwidth, and then this will go deeper into the map so we can extract more cores. And we're doing this mainly with GetSF, which has already been mentioned. And so then this is the overall population of the cores that we have now for the 15 regions. So in the cleanest maps that Fabien Louvet is working on, we have 700 cores extracted. And so here we're plotting the core mass against the deconvolved, the radius of the cores that we're extracting. For green is the young regions, orange is intermediate, red is evolved. And so we really don't see a dependence on evolution across the sample. It's, we really have a homogeneous sample in our core distribution with no dependence on evolution. And we're going down to densities, higher densities than some of the earlier work on the low mass regions or the infrared dark regions by Patricio Sanhueza. And on top of that, one of the main goals of IMF was to not be homogeneous and to not, so we don't have a dependence on distance. So if we go across the distances with the cloud mass that we're extracting, there's no dependence on our more distant protoclusters having higher masses. And so again, another CMF, but this is a preliminary one over the entire population. So again, over the global CMF, over the entire ALMA IMF core population of 700 cores is again top heavy compared to this minus 1.35 slope. And so one of the things that now I'm starting to work on is then taking the best sensitivity data that I just mentioned to go deeper into the maps compared to the cleanest. So in some cases, if we remove 50% of the bandwidth, we're losing, we've got increased noise, is to then take that B-sense to go a bit deeper. And then we're also using MNG-seg, or this multi-scale non-Gaussian segmentation that was developed in Grenoble by Jean-François Robitaille. And so that then allows us to separate the coherent and non-coherent or Gaussian structures from the map and go and then remove that a little bit more of the Gaussian noise to go even deeper into the maps. So if we go to just G353, if we look at the cleanest extraction with GetSF, we had like 57 cores or density peaks in our data. And then with the B-sense plus MNG-seg, we're then not quite doubling, but we're increasing the number of cores. So we're increasing the statistics that we can look at, and particularly, so I should point out that, well, this is the 1.3 millimeter continuum map, and the red circles here would be defined as high mass cores over 8 solar masses. White would be intermediate and black would be low mass. So we're really increasing the low mass population because we're going deeper into that noise level, and the things that would have been lost in the cleanest maps we're now starting to pick out, so we can build up those statistics. And just another example, so this is ongoing, and running these fields through MNG-seg and then GetSF is a longish process. So this is still ongoing, but towards G12, again, we are then increasing from the cleanest extraction that is in to those 700 cores we have to the B-sense plus MNG-seg. We're increasing the number of low mass cores, and already, this morning, what Enrique was mentioning, we have already seen these filamentary structures in the continuum emission where we're having cores popping out. And so now I'm starting to look at then the distribution of those cores in these regions and how we can try and characterize them. So this is just looking at minimum spanning trees, and then trying to understand from the number of, so this is the number of cores on the left-hand plot. So the blue is the original with cleanest cores extracted from these regions. And the red is with BSENS and the MNG seg. So you're seeing the number of how many cores per field. We're getting an increase. With the evolutionary sequence that we're defining with younger regions here to more evolved regions on the left-hand side. And so we're now increasing the core population. And if we look at just the Q parameter, it really, we're hovering around this 0.7. So if you think of things higher than 0.8 being more radially concentrated, where everything is more or less to somewhat level subfragmented. And so that's work still ongoing. And I just wanted to mention as well, so we have the continuum data is ready and is coming out but we also have the line data, which is still ongoing. The continuum data is one level of effort and the line data is another order of magnitude effort. We have, with the 2 bands in ALMA, 15 mosaic regions, the 12 meter, we have 7 meter in total power that we're merging. So we have these, for those interested more in the lines, we have these 12 spectral windows, 8 in band 6 and 4 in band 3. Covering a whole host of line emissions. So some of the individual key lines we're interested in are the N2H+, the 12CO, the SIO, which Alison is working on and has a poster on if you're interested. And so if we start looking at this data set, we can use this to look at hot cores in these regions. So even in the younger regions, we have at least 1 hot core typically in these in the younger end of the sample, and several hot cores in the more evolved regions. So we have this really rich line spectra in these regions, and we can really start to pull out a larger hot core population. So there's several people in the team working on the hot core catalogs and characterizing those. And then just finally, coming more into the kinematics. So, we're talking about the CMF with these top heavy CMFs, or flattened CMF. So one thing we want to do with ALMA IMF is try and understand how these accretion flows or this dynamic accretion onto these regions can affect the slope of the CMF, if this dynamic accretion can have any effect. And so with the N2H+, well, one of the very preliminary things, because these cubes are still coming out, is from the younger regions, we tend to see more diffuse, fluffier emission that hasn't really structured into these filamentary, really filamentary filaments that are accreting the material. And so with just one of the regions here, G353, here you have the continuum in the black, the moment 1 map, where you see really a lot of velocity structure in these regions. And, these, hub type filament accretion things that we've been talking about. So we really want to try and characterize this accretion flow onto these regions, but we have very complex structures. And so just in the moment 2 in the line widths, we have really, in these regions where we have several filaments, we have really broadening of our line kinematics in there. So we have several velocity streams really coming into the central hub. And so just to finish, so the data reduction is, still ongoing, but the continuum is ready. There's a lot of nice figures already on the website, so I'd encourage you to go there. If you have ALMA data that, we really spend a lot of time developing this pipeline, which can work on the ALMA data, and it's reproducible. Everything we've done to the data is going to be documented. And so this will then provide us really, just to point out here that ALMA IMF will provide the community with really an unprecedented database of high legacy value products that we can look at the filaments, the cores, hot cores, outflows and inflows. And, we're already starting to see these, kinematics and accretion flows that we really want to characterize more. So I'll finish there and take any questions. Thank you.
Any local questions from the audience? No? Yeah, I do. Oh, okay. Lee first, of course.
So there was a question in the last talk about what's a core. And I could imagine that superposition might affect the CMF. And so my question is basically, are there plans to take somebody's simulations and look at what the bias might be?
Yes, so that's it's part of the EcoGal project. That's one of the key tasks. So with Patrick, this is something we plan to do with his simulations and put them through, well, try and make them the same as the observations, put them through SimObserve and ALMA, and really try and compare as closely as we can to see the effects from the simulations. So that's one of the main goals as well.
What's actually done already by Fabian Rouget in the paper, we have that simulation observation.
Okay. And I had another question. You said that there's no real signature of an age dependent on the mass and size distribution. So what is the range of ages that you're considering there? Do you have any clue, or you just classify them into young and not so young? But do you have any idea of what is the range of ages?
No, so yeah, we're classifying them based on the sequence that Thomas mentioned, just if they're infrared bright with the free emission, but we don't have really an age, a true age estimate. I mean, I'm not 100% sure to give you an age estimate of them.
Yeah, basically, I think what would be very important is to determine whether the spread in ages is a few 100,000 years or maybe a few mega years, something like that, in order to determine whether you expect any significant evolution in the gaseous phase compared to the evolution in the stellar component.
Yeah, I mean, so it's difficult to it's a difficult thing to age them as well, because even within the clusters themselves, because we are sampling quite a large, when we're doing mosaics, so we have in some regions the H2 regions, and then off to the side of them something that looks a lot younger. It's infrared dark. It's not maybe kinematically joined to the other part of that cluster. So it's a difficult task to do, but it's something that we should think about.
No online questions yet? No? If so, we thank Nicole again, and now we have the videos from the poster presentations.